Okay, here we go. Chapter 1.6, nested quantifiers. Okay, so nested, meaning that there's, you can see them intertwined. So I'll just here basically talk a little bit about it. So here we have for every x and for every y, p of xy. So here there's going to be two things, two objects from possibly different domains of, and we usually restrict it to one domain, but it could be from anywhere. And so let's go through some examples. So here we go. Example 1.61, it says restate for every m there exists an n such that m is less than n in words. Okay, so, and the domain of discourse here is the set x cross x, and then the solution would be basically what I just said, I guess. For every m there exists an n such that m is less than n. Less formally, this means that if you take an m, whatsoever, okay, any m, then there is an integer n greater than m, period. Okay, let's take a look at another example here. Consider this statement. So this says for every x and for every y, x is greater than 0 and y is greater than 0 implies, right, x plus y is greater than 0. Okay. So this statement we can try to give an assessment of truth, right? I mean, so the domain is r cross r. This statement is true, right? Because, for every real number, if you take a real number that's greater than 0 and another real number that's greater than 0, if you add them together, that's greater than 0. So that's a true statement. Here's another one. Consider the statement, for every x, for every y, x greater than 0 and y less than 0 implies x plus y is not equal to 0. Well, this statement is false because you could just take, here's an example or counterexample. Just take x equal to 1 and y equal to -1. Then they add up to be equal to 0. So that makes that statement, this entire statement, false. Okay. All right, let's take a look. Here we go. Example 1.6.6. Consider the statement, for every x there exists a y such that x plus y equals 0. Well, yes, this is true because this is, so for each x, you pick an x, fix an x, and then you have to exhibit the existence of a y that adds up to 0. Well, that's the additive inverse, right? Namely, for x, you just plug in negative x, and then we know that x plus negative x is 0. Okay? Let's see, look at another one. Here, let's look at this one. This example here. Consider the statement, there exists an x such that for every y, x is less than or equal to y. Now, we need to know what the domain here is, but now look at it. The domain of discourse are the positive integers, right? And so in that domain, this is a true statement because we simply take the smallest integer and let that be x, namely 1. All right. Now, if we change the domain of discourse to say the real numbers cross the real numbers, well, then this statement would be false. Okay, so it's important to always consider what you're talking about with these statements. What is the set that you're thinking about? Okay. And yeah, that should do it. I mean, I've assigned some problems in 1.6 that you want to take a look at, and that'll help you to get used to the idea of nested quantifiers, because they do come up quite a bit in mathematics and in basically many things. So, okay, thank you. Hopefully that helps.